Okay, queuing systems. We are into queuing system extensions. Before I get started with some of our different applications, I wanted to share a note. If you have an MM1K queue, these equations only work for S equals 1. So you can use this when you have one server, but if you have more than one server, the equations are going to be different. So that's a note from last time. Okay. Let's get on to today. MG1. MG1. This is a system with general service time. What does that mean? Well, there are no restrictions on the service time distribution. So it can be normally distributed, it can be uniformly distributed, but it's something where the service time distribution is not necessarily Markovian. So what do you need? Your service rate and your variance according to whatever the distribution is. You still have a Markovian arrival rate, an exponentially distributed arrival rate. Now you got some service rate mu that has a variance of sigma squared. Okay, so how do the equations work on this? Well, you still have your utilization rate of lambda over mu. That hasn't changed. And our P naught, our probability of being in state 0, is still 1 over lambda over mu. But LQ, a little bit different. Now we are taking into account the variance as well. So LQ is the easiest one to figure out first. And from LQ, you can solve for WQ, average number of, or average wait time in the queue. You can have your equation for L. Once you've got LQ, it's just rho plus LQ. And you've got W as well, your average time spent in the system by each customer. So here are your 4 equations that you need to analyze these MG1 queues. Okay, side 2. Now, what if your variance is 0? What does that mean? Well, now we have an MD1. D being degenerate. It just means that the service times are constant. So we can still use the MG1 equations because it's just a special case. But sigma, the standard deviation, sigma squared is 0. So LQ is just this, which is the same as LQ for an MG1, but without the variance term. And that's it. Okay, one more, Erlang. Erlang is an M, EK, 1. So what is EK talking about? Well, in an Erlang, in a system where we're going to use the Erlang, you have K subprocesses in your service. So it's K tasks that have to happen sequentially. So let's say you walk into a coffee shop and there's only one person working, and that person is going to take your order and then make your order and then doll it up to serve it to you. So they're going to put the coffee jacket on and put the whipped cream on top or whatever else they're going to do. So let's call those 3 separate processes. And the service rate for each of those sub-processes is mu single. We're making the brash assumption that you have the same mu single for each of these sequential sub-processes. So a little bit counterintuitive, and the assumptions might be a little shaky for a lot of real-world systems, but this is what the model looks like. So for example, in a coffee shop example, where let's say you have 3 sub-processes, and each of the sub-processes has a rate of 10 per hour. Now your rate for the whole system is just going to be the rate for one of the sub-processes divided by K. So in this case, you're going to process 10/3 per hour. So it's 3 times as slow as the rate for just a single sub-process. And you're assuming that the next customer cannot start into the service process until the previous one exits. So it's not like Starbucks where you walk in and somebody takes your order, and while yours is getting made, they're taking the next order. This entire thing is sequential. The variance is just going to be K over mu single squared, so the service rate squared. So in this case, it's 3 over 100. These are exponential service times for these sub-processes. And now we can use the MG1 equations. So we have, these are the exact same ones we were using before, LQ, L, WQ, and W. and you can just plug your numbers in and solve. And in this example, we don't have our arrival rate, so you can try this out if you like.